Giuseppe, good morning.
Hello, everyone, and good morning.
Good
Can you hear
morning.
me?
We can hear you perfectly. Yes. Thank you very much for joining. Where are you dialing in from?
Sorry? Oh, I'm joining from Amsterdam. You might be able now. I see it's too white, but you might be able to admire the wonderful Dutch weather right now, which is mostly, well, gray and and rainy.
Grey and overcast. Yeah, that's because we robbed all the sun here in Dublin. Dublin is having a very, very sunny morning. Okay, so Giuseppe, you are CTO and owner of Hoppinger, and you're going to talk to us today. And this is a mouthful: functional programming principles applied to the architecture of React applications.
That is
Fantastic.
correct.
Okay, so if you want to share your screen, take it away, and we'll catch up afterwards for a Q&A.
Yes, very good. Now, let's make sure that my screen is sharing properly. Is that the case? Can you see my screen?
Yes,
Yes, you can. Very good. All right, I'll take it away. So, first of all, it's a pleasure being here. Hello, everyone. Let me start with a quick introduction about myself. I'm Giuseppe Maggiore. I have a relatively long background in computer science. I started programming about 22, 23 years ago. Fascinated by the elegance of code and the elegance of turning ideas into something that a machine can actually execute, but at the same time, also annoyed greatly by the constant brokenness of everything. Today's session will actually be focused on these two aspects, elegance versus brokenness. In particular, I want to introduce React from a new perspective, the perspective of functional programming. The idea is that we're going to manage our flows of data in a very explicit way. And this explicitness will allow us to add more meaningful types. It will allow us to improve composability and achieve code which is more explicit in its most complicated aspects, namely the management of state, more reliable because of this explicitness, and to an extent, at least in my own very personal opinion, more elegant. And by doing so, we will also stumble on a generic library of reusable front-end abstract components and combinators. And I can imagine that someone might also ask, okay, but is this just a sort of academic talk, or is there some applicability to this? Obviously, your mileage may vary, but let me tell you that my company has been using this sort of constructs, we call it the React widget library, for the last half a decade with great satisfaction. The number of defects in our front ends has basically turned to zero, at least the technical defects, stuff that's avoidable. And at the same time, the velocity at which developers can build code has gone up, and the ability to share components between projects has also increased dramatically. So once again, everything is a matter of subjective taste, but I can at least attest to my own personal experience. What I'm going to show you works in practice and does add to the bottom line. Okay, now, we don't really have much time, but I greatly prefer live coding. I think it's a lot more aligned with the creative process of discovery, even though it does come with the risk of of making mistakes. And so let's go for it. This little application I have is just a very basic. It's just a very basic sort of little hello world. Let me delete the code I have prepared, and let me see. Let me check that everything runs properly, that we actually have, an application that does something. Okay, there we go. So we are able to start. Okay, so let's have a sort of let's have a case study. Let's say we have to model some counters. Okay, it's like the most basic hello world that you can imagine. And let me start by defining a counter state. Okay. And this counter state will simply, contain just a count, and the count is unsurprisingly a number. Now, what I also like to do is to explicitly model the updaters, the things that change the state. So the counter state updaters, and the counter state updaters, there's only one field, so there's only going to be one single updater. And So for this, I will already start using functional programming constructs. So in particular, let's define a function. That's handy to have this as a reusable type definition. And a function from, well, an input to an output is simply, well, a wrapper around, no, not even a wrapper, just an alias around the lambda from that input to that output. But now I want to define an updater over a given state. An updater over a given state is a function that takes as input the previous state and returns the new state that has been, therefore, updated. Okay? Very good. So in order to update a counter, well, what are we going to get? Well, we're going to get the inner updater. I will just call it underscore. And this is an updater over the number, so whatever we want to happen to this count. And mind you, there might be also other stuff like x, y, etc. in this state. So yeah, we are only focusing on what happens to the number inside the count field. Okay, and the count updater takes as input the updater over the field and returns an updater over the counter state. So this is a form of, you could say, we are embedding this updater of the number over an updater of the broader counter state. So we take as input the current state. I like to call this S0 because it sort of reminds, the idea of right now, this is the state at time 0, so the state now, and we're going to build a state 1 or the state at the next point in time. And this will simply be the same previous state, but the count has been updated by invoking the updater function over s0.count, be it increase, decrease, put to 0, whatever, we don't know, we don't care. Now that we have this basic setup of our state and our updaters, let me just copy from my backup file the definition of our counter, just because I don't want to bore you all to death by typing this very trivial little React counter. We have our counter, and it's a React component. It takes as properties the counter state, which is meant as the initial state. The properties might also be more articulated, but for this particular example, we don't care. And the state is the counter state. So you can see that in the constructor, we just initialize the state to the properties. In the renderer, well, you can see that this is only just a button. In the onClick event, what we do is simply we call set state, and the set state will take as input a function from counter state to counter state. So you can see this is TypeScript, so everything is compiling. Well, let me go to the new line, then we can see a little bit better. Yes. Okay, and you can see that we call the counter state updaters over count with a simple increment function. So this increment function will be applied to the value of the count of the current state. And then in the button, oh, by the way, I'm not really an artist, let's say, in the aesthetic sense. So the demo is not going to be pretty by any stretch of the imagination. I'm not even going to try, just for your information. But anyway, so here we can show the current value of the count and then +1, which sort of more or less is suggesting that, yeah, okay, we're going to increment. And now in the render, we can actually put 2 counters. Okay, so we can put, well, start with just one counter. And, oh, did I just change? Yeah, okay, we start with a counter at 0. We can also put another counter, again, at 0. Now, the application is not very exciting. There are 2 counters, and they are both managing their state, as you could expect. All right? Now, let's introduce a problematic scenario. The designer of this application has talked to the client, and the client would tells us about a new business rule. And in particular, the business rule is that the value of the first counter may never be equal to the value of the previous counter -3. Okay. That's a problem, because both counters right now can only see their own state. And because they're hiding the state, we've created a situation where it's very, very impossible to build any coordination. But here's the thing. Okay, again, based on personal experience, but the more an application grows, the more the components of the application have to gain the intelligence to cooperate with each other. And cooperate simply means that they coordinate their state changes in a rich way. So this concept is going to be the thing that we're going to try to fix according to the principle of functional programming. As you know from the documentation of React, Facebook does, the makers of React, as you all know, Facebook does strongly recommend that we use functional components. And functional components in React can actually be generalized with a very specific signature. So let's say that we have a functional component. I actually like to call these streams because they are sort of data streams, and they are generic because, well, the kind of state that they update can be anything we want depending on the component. And a stream, it only has basically a stream a run function. Now this run function will eventually return a JSX.element because this is akin to the render function. Whether we call it render, run, whatever, the names are not that exciting. And what does run take in order to signal, according to the principle of functional components, that it wants to change the state? Well, it's going to give us a callback. It's going to get a callback and it's going to invoke it. A callback that simply takes as input an instance of the state. This is the new state, and it doesn't need to return anything. And so this run function, it takes as input a callback, which is, let's say, on on change, and well, our component our stream will be tasked with calling on change with the new value of the state or O of the output it wants to propagate, and then it may render whatever it wants. Some of you might notice that this is very, very similar to a very old concept from functional programming, because someone might even consider this to be a sort of continuation passing style, and the callback is something that in functional programming has been known for literally decades. I think the first mentions of CPS were in Lisp, probably like 40 or 50 years ago. So that's interesting to see these things coming back. Okay, so this is a stream. Let me make sure that I'm still aligned to I'm still aligned to my own sample, because I wanted the ability, to actually copy paste the stuff in case I make any mistakes. And yes, this looks like the case. Oh, what I did, I also defined the stream runner as something that takes as input on output the callback and returns a JSX.element. Very good. And the stream is simply a wrapper on top of a stream runner for now. Okay, very good. So now what we can do is we can define a constructor of a stream based on a stream runner. So let's do this. And yeah, actually, I'm also going to copy this, because this constructor simply in order to create a stream from a stream runner, well, for now we just encapsulate this. We just encapsulate the run function, but this is handy because we are going to add more later to our stream. This way we can have this whole algebra of composable components. So for now, the stream runner and the stream are basically the same, but later they will differ. So the stream runner is, let's say, the basic functional component in React, but the stream will be our own composable object. Okay, so we have the stream, and well, the stream now starts looking, the stream constructor takes as input this stream runner, encapsulates with the stream. So let's move on and indeed define our little counter. Oh, so let's define our little counter by invoking. Okay, so what I'm doing here when defining a single counter is I'm calling my stream constructor, which is just its wrapper. This bit here is very close to vanilla React. You could even consider the onChange function to be the equivalent of setState. We could call it setState if we wanted to highlight the conceptual similarity between this callback that we have to change and the fact that this callback is changed in order to request a state change. But I do prefer onChange because I think it's a bit closer to the reality of what a stream does. So a stream requests a state change, but does not maintain the state itself, so it can't guarantee that the state change is accepted. So the state change is simply propagated to whoever the parent is. Notice that I've also introduced another interface, which is an IO stream, which is a function that takes as input. Okay, this could also be called the state. Let's actually rename this. Parameter. Okay, so this is the state S, and an IO stream, which is the most common sort of functional stream, takes as input the current state and returns a stream, and the output of the stream is this updater. This is something I find particularly elegant. So the output of the stream is not the new state, but rather a function that will be able to perform the desired change in state. The power of using an updater, because we could also say, okay, we pass the new stream, that we pass the new state as output to the onChange callback. But this is less composable, because if you have two updaters, because of concurrency, two updaters can always be composed together. First, you have the state, you run one updater, you get a new state, you run the second updater, and you get the new state. So this is a lot more robust when you have things that act with a delay, for example, when dealing with asynchronous code, high degrees of concurrency, promises with real-world latency, etc. Okay. So now we have our counter, and our counter basically takes as input the state and propagates a state change wish. We can't really use the counter yet because, well, we need to encapsulate it in a container, which is the root of a React application, of a React application built according to this principle of functional programming. And this root container is the only container that is stateful. And this terminology container component is also something that we do find back in React's documentation. And the idea is that you have a root container because, well, the application has one state, which is contained at the root level, and then it has a bunch of components that are all nested and connected to each other in powerful and elegant ways. Now, I will pick my implementation of the state container, and then we will look at it later. Okay, so I think this should be enough. Okay, now, what does our state container do? The state container takes as input. Well, first of all, it's generic in the state that it contains. It takes as input, the initial state, because this bootstraps the whole application. It takes as input a non-state change callback, because also the state container might be composed into other things, even though this can lead to rather unpredictable code. But most importantly, it takes as input an inner stream, and the inner stream is one of our IO streams. I notice now this could also be refactored to just an IO stream of S. Okay, so we start with the state, and this gets the initial state from the properties. And then in the render method, what do? Well, we simply call the inner stream, because the inner stream is the actual logic. We pass to the inner stream the current state, and then we say, okay, run, because the run method is not ever going to be called explicitly, but in the state container and some other combinators. And whenever and to run, we pass a callback, because whenever the inner stream wishes to signal a state change, what do? Well, we invoke set state with this state change or state updater. And then when the state updater is done, I may call on state change to further propagate whatever happened to the state after invoking this state updater. So you can see basically the inner stream takes as input the current state, and whenever it calls the callback state updater, well, we simply pass the state updater to set state, so that we may actually save the new state via set state into the state container. Okay, at this point, it should be possible to actually have a state container. Make sure that the commas are happy. Oh. No. Okay, so the initial state will be the initial. I've changed the, okay. Yeah, will be will be the initial counter state. So const initial counter state, which is a counter state. I always like to simply have a proper definition of a state, the type, the initial value, and its updater. So I just find it slightly cleaner. Okay, so we have an initial counter state, then we have an on-state change. Let's say just for debugging purposes, this is simply console.log. We just want to see the new state. And finally, we have the inner stream. And what is the inner stream going to be? The inner stream is going to be our counter. Okay, everything compiles. Because, well, by the initial counter state, then it's forced what the counter is supposed to be, which is just an IO stream of counter state. So everything seems to work now. And here we go. Okay, and we see, well, that the thing is saving its changes. It's applying its state. You can see, well, that the console.log is being invoked by the state change. In practice, the only actual use that we do at my company for this kind of callback on state change at the level of the state container is just console.log in order to debug the application. Very often you will see something like this, which is even more common when the application doesn't need to be debugged. But yeah, it's handy to always have a sort of indeed a little debugging hook. Okay, now things actually get interesting. Well, first of all, let's clean things up a little bit, because I want to expose a distinction between the things that belong to what you could call our application, our domain, and the things that belong to a sort of general utilities. So these are all the utilities, or the definition of composable streams. And you can imagine that in a professional context, in a professional application, everything that I'm scrolling through now, including the state container, is not part of our application. So this is the end of the utilities, and this could even go in we keep it in a separate package, as a matter of fact, but at the very least, separate files. This is the actual application, and this is specific. It has a specific state definition, etc. Whereas the code of the utilities is generic, is general purpose, can be used for any application. Okay, now, but remember, our challenge was we want to have multiple counters, and we want to be able to synchronize those multiple counters so that the two counts of the two counters are compatible with each other to avoid our bug. Okay, so we have one counter, but let's define now the state of the whole application, which will be I will call it, it's not a spectacular domain this, but I will call it the counter state, and we have counter 1, which, well, it's a counter, so it has a counter state, and counter 2, which is a counter state. Okay, now then the initial counters state will have counter 1, which, well, starts as the initial counter state, and counter 2. So we start them both at 0. And this is also the other initial counter state. Then the counters state updaters. Okay, now the updater for counter 1, it will take as input. Oh, and by the way, this whole signature can be, this whole thing can be automated thanks to TypeScript's awesome type system, but we're not going to do it today because that would take like an hour and a half, but that's beautiful. Anyway, just so you know. So the counter 1, it takes as input of an updater of the counter state. So what needs to be changed on the counter state inside counter 1, and it embeds this input in the counter state. And when we want to perform a transformation of the counter 1 state, what's going to happen? Well, we keep S0 as is. Specifically, we keep counter 2 as is, but the counter 1 becomes underscore of S0.counter1. And then the updater for counter 2, well, it will perform this update over the counter state on counter 2 and put the result in counter 1. This is slightly error prone, so you could make a mistake. This mistake is possible. That's the reason why I do prefer to try to automate this so that the type checker does most of the heavy lifting for us by specifying, this label here only once. And it takes a surprising amount of sophistication at the type system level, for the record, in order to be able to achieve this. But TypeScript does have that. TypeScript really is an awesome language. I was mind blown when I discovered it. Okay, so now, okay, one could say, okay, the initial counters state, that's very good, but then the inner stream, this doesn't work anymore because this inner stream now only works on a single counter state, but we've just told the state container, hey, you're going to deal with this double counter state, the counters state. So how do we compose multiple, in our case, counters, so that they sort of run in parallel? And there's this combinator, which is called the which is the sum combinator. Also sort of funny because, well, for those who have studied functional programming and category theory at an academic level, just so you know, the stream we built happens to be a functor. And it's a functor that also supports an algebra. And part of this algebra also includes sum, product. I don't know about exponentiation, actually, but yeah, there's so the fact that you recognize it as a functor opens up a huge amount of possibilities to building a library around these things. Okay, but the most interesting bit is that, well, we want to have this combinator. I like to call this any, which basically takes as input an array of streams and compacts them into just one stream. Okay, so let's say we have an array of streams of this, all with the same output. The streams all have to have the same output, and we just squish them down to a single stream. Why? Because, well, basically we're going to run all of these streams in parallel. The first stream that says, hey, I have a new state, that new state is the one that the any combinator will propagate. Now, let me see. Okay, so now I have to provide a stream runner because this is a low-level combinator, so we have to actually build it from scratch. Well, this is... wait, what did we call it? I want to have the same terminology. On output, yes. So this stream has its own on output, and then it's going to put all of the underlying streams. It's going to run them all. So streams.map, then for each stream, what do? We run the stream, and, well, when the stream says, hey, I have a new state, pum, we just tell the stream, okay, then call on output. So basically, we're giving the same on output function, on output callback to every one of the streams, and the first stream that wakes up and says, hey, I'm done, then the any combinator propagates that, and the others, well, they just keep quiet, they keep silent. So one might be tempted to say, okay, we're there, almost, and we really are. Okay, so we could have two counters, but no, this doesn't work. It doesn't work because because this inner stream and this any combinator is supposed to work on our counters state, but the inner counters, well, they have the wrong type because the counters still only know how to deal. They only know how to deal with the they only know how to deal with a single counter state. Also, by the way, I was about to forget, but the inner stream will take as input a current state. Yes, very good. Now, this current state will be a counter state, but any expects two streams that have to produce a single counter state. We can, well, the counters do expect a counter state, so this we can this we can fix right away. We can say, okay, the current state.counter1 is passed to the first counter, and current state.counter2 is passed to the second. But what those two counters return now, and that simply is wrong, because okay, I'm going to do something that is absolutely not allowed. I could say, okay, this is let's cast this as a stream of counters state, but no, this doesn't work because the callback of these counters simply has the wrong shape. Okay. We can exit this impasse by making the functoriality of the stream more explicit. Now, that's a terrible and very academic sounding sentence. It simply means that a stream can be given a map function, and I will just copy the definition of the map function here. Okay, what does map do to a stream? A stream produces, in general, an output O, of type O. So a stream has its own output. So it says, oh, this is my state, and this is the state or the event that it wants to propagate. But what if we were to get a function as input that is capable of turning one instance of the output O into some new type, new O, by some magic? So this function can then be put as an output filter on top of a stream, so that we started from a stream of O, but we get a stream of a new O, another type. So every output of the stream, before being propagated, actually gets transformed by this function. Okay, well, then we need to implement this. And I'm just going to copy this from my little nodes. Now let's take a look at what map does. Take this function that operates on the current stream of type O. We have a function from O to the new O, and now we have to produce a new stream. And this is, you could see this as a synthetic stream, if you will, that processes, that propagates the new output. What do we do? Well, we create the new stream, and this new stream has a non-output that processes this new O. But our underlying stream, this, when we run it, it tells us, it gives us instances of O of the previous state. But by calling f of O, we go from the previous state to the new state, and this new state may be propagated to this synthetic callback. And the result, quite simply, is that we can map a stream, and now we have to produce something that turns our updater of counter state into an updater of counter state. And well, we actually have this already. This is counter 1, and this is counter 2. Oh, okay, let's see what's happened. So this counter over counter 1, it produces a counter state. It's an updater of counter state. And this updater of counter state, well, now we have to decide whether or not it goes into counter 1 or counter 2. So what we say is, okay, whenever you produce this updater, let's give this updater to counter 1. And counter 1, look, it takes as input an updater over the single counter state, and returns an updater over both counters state. And the second, well, it does exactly the same. Now, let's take a look at whether or not everything is broken. Well, at least it hasn't blown up, so that is good. And well, we still have our debugging function. Okay, but now it's time to add our validation logic. Okay, now our validation logic is going to refuse a state update unless it matches. It's going to refuse a state update if a given condition if a given invalidity condition is met. So let's say we have validate. Validate will take as input the old state, the current state. Now let's call this S0, the current state, and this is the counter state. It's going to get the new state that we would like to produce but haven't produced yet, and we'll pick the right one based on its validation logic. And very simply, what we're going to do is we're going to state that if S1, the new one, counter1.count is equal to S1.counter2.count minus 3. I think this was our logic. Again, this is not really a reflection of exactly what a validation would look like in this scenario, but you can imagine that we just need counter 1 and counter 2 to somehow be kept coordinated or aligned. Okay, so if this is the case, S1.counter1.count is equal to counter2.count minus 3, then we discard the state change, so we return the old state. Otherwise, we return S1, so the new state. Okay, and at this point, we can simply call validate. We give the old state, the new state, and let's do it in both cases. We could also just say no, we use it only in one place. Wait, is there an error? What did I break? Oh, I'm missing a, oh, how embarrassing, a bracket missing. Okay, now let's see what happens. So this is 1, 1, 2, 3. Oh no, something is not working as it should. Let's see. Right. Okay, very good. So yeah, it was the other way around, and you can see that we have achieved this coordination between the two states. So when I press this second counter, the validate function is producing whatever it needs to produce. Now, in a real life scenario, you could also have like something like the latest error, which is optional, and then if validate has failed, then we could say then we could also propagate, the error by saying, okay, the latest error is cannot be, so counter 1, 3, blah blah blah, and otherwise we simply reset the error when performing the validation. So we could say, okay, latest error is undefined, and this way we could also obviously show the error somewhere on the front end. But I mean, for now, let this be sufficient. Now, I can imagine this has been a lot of information very quickly. Let me also move this to our set of general purpose utilities. Now, first of all, I would like to point out that we could split this application obviously much better, because you could imagine that this counter here goes in a single file, the counter, but the composition of counters, so the counters component, would also go in another file. And what we do usually in production is we separate the state with these updaters from the stream itself, because it makes sense. And in real life, we also split the front and the layout of the component, so that the layout, the state, and the logic of composition of the state are neatly split. So this also allows people to work in parallel without mixing the work of the people who are focused on HTML and CSS, for example, from the work of the people who are focused on the actual state management, achieving also, less merge conflicts, less merge issues, etc., which is a nice bonus. But especially what I particularly love about this is that if you look at the counter, it's saying very, very clearly by the types what it does. So if you want to use a counter, you have to explicitly pass it a state, and you also have to know what to do with the counter state. And because everything is based on these updaters rather than just propagating a new state, concurrency issues, so an old state is stuck in a closure, and a promise forces that old state to be sort of incorrectly be called back to life, canceling some other updates. So these are super nasty bugs that in this framework can't be achieved anymore. But the thing I like the most is our ability to define combinators like any. In our library, we have a few dozens of these, and some of these combinators can be gigantic, because you can also build proper higher order components where the definition of the state is really solid, like type safe routing components, type safe CMS building block components, etc. And you can build your application into, or better yet, your toolkit along two directions. One direction is building more and more of these abstract combinators like any, for example, combinators that manage asynchronous API calls with proper retrying, with caching, etc. And you can make all of that transparent to the containing application, which is really good news. And at the same time, you can build these little components here and reuse them wherever you want, because these components are heavily reusable by virtue of the fact that they do not maintain their own internal state. And so they can't do something hidden inside that you can't change with custom validation, etc., should the need arise. I promised in the beginning that we would try to manage data flows explicitly, and that is what streams do. They manage the data flow of a React component in a very explicit way, in a way that is more type safe, with types that are therefore more expressive. So you've seen that a wrong composition like this one actually gives a compiler error, which, helps a bit, because compilers are better than humans at tracking lots of information. Improve composability, because something like any is an algebraic, any and map are algebraic combinators, which are proven in the last, I think, half a century to be some of the most fundamental combinators when trying to achieve general purpose composability. And finally, the fact that we would slowly lay down the foundation for a growing generic library of reusable front-end abstract combinators. And by abstract combinators, I mean indeed all of these things with all of these generic types that make them applicable independently of the concrete shape of the state and the concrete requirements of your application. This said, well, we do have a few minutes for the Q&A. Oh, yeah, I'm going to share this terrible thing. No, yeah, thank you very much.
Excellent. Thank you very much, Giuseppe. That was fantastic. You actually had me paying attention all the way through, which for me, I don't have a good attention span, and to see you code was very engaging. So well done. That was good.
Thank you very much.
So yeah, is the code available online? Are you going to stick it up somewhere?
Oh, wait a second. Shall I just?
You can do it afterwards, and then you can stick it into the chat channel.
You know what? I'm going to do something ugly, but well, there you go.
That's okay. Well, you're not sharing your screen anymore, so we didn't.
No, but I just put it in the chat.
Oh, perfect. Excellent.
Like, faster than this.
It's quite a subjective topic, I think, using functional coding, and there are different ways to do different things, and people have their preferences. I guess a question for me: how do you feel your concept was? Do you think it was displayed well in a small Hello World program, or do you really need to see this at the bigger sense to really get the power of what you're doing?
That is indeed, yeah. That's a very good question. I think if you know these, okay, so if you know already the basics of functional programming, seeing these primitives in action on a small scale can help you bridge the gap between vanilla React programming and some literature on functional programming, which is well known to be very powerful, but not immediately applicable. But that is, let's say, an advanced application. For most of my developers, we're about 40 developers in my company and 100 people in general. And for most of my developers, the click really happens when they see bigger things, especially when there's a lot of asynchronous code running, multiple promises, and maybe you have some promises that call an API that is very slow, that gives you an answer after 5 seconds, but one every 100 calls. And then you have these very nasty concurrency issues to debug. When they see that these things stop happening, they just don't happen anymore, that's when they're sold, usually. But indeed, there's a threshold, and the threshold is objectively high, yes.
Yeah, no, that makes sense to me, because a lot of these concepts, you really need them in your muscle memory. They need to be simple, and then you need to see them in the wild to fully appreciate what's going on.
Yeah.
I'll go to some of the questions that have been passed in. This is along the same theme. There's a 2-part question. I understand your goal, keep benefits of React class, but here it looks like you are re-implementing use state hook. Wouldn't it be easier to keep functional React components?
Almost. It's actually very I love this question. It looks a lot like use state, indeed. So funnily enough, the callback I used, you could rename it to use state. The difference, though, is that functional components with use state, they don't change the type of the functional components itself. So you can't see the type of the state, and the state is still hidden inside the component. So it means that if you have 2 functional components that use the state hook, it will not be immediately evident how to coordinate their states. So the state is still hidden inside the component, and you can't see from the signature, from the type signature of the component, what state it manipulates. Whereas with the streams we've built today, the state the stream manipulates is this generic parameter, stream of O, and that is made very clear so that you can also say, when building, let's say, a higher order application, you could say, here I only accept a stream that manipulates a given state. Whereas with use state, all of your components, they have a signature JSX.element or something similar, which doesn't say anything about what state they manipulate. So it is, yeah, so it's very similar. Yeah.
I've actually a question on top of that, because you did use generics and you mentioned your love for TypeScript. You didn't say that I don't know if you said love, but you definitely shared a preference for TypeScript. If you didn't have TypeScript and generics, would you still go with the same pattern?
Well, you would lose one of the big advantages, which is making it very clear. Let's say you're building, I don't know, you need your own generic framework for forms because your company builds forms and you want to build your own flavor of generic combinators. Losing the type safety and the ability to get a compiler error if one of the users of your generic forms is manipulating the wrong state, that is a big missed chance. At the same time, the example we've seen today, that you have two components and they have their own state, but you want to look at both states to keep them coordinated. If the state is inside the component, you have a problem anyway. So what we've seen, 50% of the advantage is making the states, really pulling the states out of the components. And doing that is still advantageous, because then you make the states local and neat and clean inside the component, but at the same time, you also force the component to state clearly what happens to its internals, so that you can coordinate it in case the need were to arise.
Okay, very good. The question I have up, there's actually two parts of that. Second part to that, I should say. I'm not sure if this needs to be clarified or if it's already been answered. And component can have class manager. In this case, they'll have the benefits of React Evolution, but still have class components, etc. Is this just an extension of the question we previously answered?
I think this is just an extension. Yeah. I think we sort of covered it.
Let's move on. Where do you recommend someone start learning about functional programming? I would say Google. Put it into Google.
Yes, Google. Oh, wait a second. Let me check something very quickly. Yes. Okay. Now, this guy here, I'm going to put something in the. I just put it in the chat. Bartosz Milewski. He has one of the most elegant courses on category theory and functional programming that can be directly translated into what we've seen today. He does talk a lot about Haskell, but that's completely irrelevant. He's not a Haskell fanboy, and he has a lot of experience. He started like I did on C++, and I guess people who start with C++, they've seen things crash and burn so often that you really develop a flavor for stuff that doesn't break that much. This guy has made a difference, at least for me.
Yeah, good. I liked the Haskell reference. It kind of reminds me of something I say sometimes. It shocks people. I say the best JavaScript developers are those who don't program JavaScript.
But Haskell.
Yes, or similar. Okay, move on to this question here. Hey, Giuseppe, can you tell us about Valto architecture? Valto turns the object, you pass it into a self-aware proxy. I like the question, and then the person answers the question afterwards. So, yeah.
Thank you, because I have no clue what Valto is. I'm really sorry.
Okay. Perfect. You know what? I've no idea what it was either. I was hoping that you'd enlighten me. Okay, so that's one for users to Google as well.
But I do like the second part of this question, because what we have done today is basically making sure that the objects we have, our components, they are self-aware proxies, because they proxy all the state changes are proxied through the object. The object can call set state, but the set state doesn't happen right away immediately in a state that is buried deep inside the object itself. But yeah, it is a proxy of its own state changes. So I hope to infer that we might have done something similar today, but I have to admit my own ignorance when it comes to Valtio.
Okay, no problem. And I have one question to add in, which is, as you were programming, if I was to do what you did, is ensure state between components, using React context is kind of shouting at me. So why not just use React context to share state?
Well, actually, context is also, according to React's documentation, context is intrinsically not statically typed, so that would lose the benefit of type safety. Because one of my personal goals is to be able to get a junior developer, give them a component and say, hey, if the state of your component doesn't match the expectation of the application, this thing is going to break. And I want the compiler to guarantee this. By using the context, you could, the context is sort of a big global shared state. So that's okay. You can also build some very interesting libraries with it. It doesn't have the safety properties that we've seen today at the type level. So you could achieve something very similar to what I've done, but in a way that's hidden. And also the documentation of React does state explicitly, whatever you do to the context, you do at your own peril, because we reserve the freedom, to change the way the context behaves at any given time. So that is, it's doable. It will work today, but not type safe. And yeah, God knows what happens in a couple of years. But it would be similar. Yes.
Okay, I like that answer. I like specifically you said good for junior developers. And I think we may be like-minded in this, in that if we just assume we're experienced developers. Let's just pretend we're experienced developers. I think one of the most important things for experienced developers to do is write code that junior developers can understand. It's all about safety and not going OTT. And I like that in combination with the functional style, because it's very common for functional programmers to go crazy and show off and play with their toys, whereas this is about keeping things safe and making it easier for developers. Perfect.
Thank you. Couldn't have said this better myself. That's.
Oh, I was afraid I couldn't be putting words into your mouth, but no, definitely. Okay, fantastic, Giuseppe. That's been brilliant. Thank you very much for joining us. So we'll say goodbye. Thank you.
Thank you so much, and thank everyone for tuning in and listening.